Good afternoon, everybody. My name is Michelle Mahove, like you previously said. I'm from the University of the Witwatersrand in Johannesburg, and today I'll be giving a presentation on my master's work based on the use of phylogenetic biodiversity metrics in the conservation field. And in order to effectively conserve biodiversity, we need to be able to efficiently measure it, because you can't protect what you don't know and you can't know what you can't measure. So the conservation field, as we all know, suffers from a lack of time and resources for biodiversity measurements. Therefore, effectiveness is of utmost importance. Biodiversity metrics are a useful tool for measurements, and traditionally, species metrics have been utilized. And these species metrics are metrics that focus on the species level of biodiversity. The most common of these metrics are species richness and endemism, and species richness is the number of species in a specified area, while endemism is the geographic restriction of a species. And these traditional approaches give us information on the biodiversity and endemism of an area, and they form the basis of many ecological hypotheses. An example is the intermediate disturbance hypothesis, and they are relatively simple to use as well as good biodiversity indicators in many cases. However, there are shortcomings. For example, they are affected by sampling bias, taxonomic uncertainty and change, as well as that there is no universal species concept. The most common flaw, however, is that they do not include evolutionary history of taxa. Biodiversity is not only about species. There are many facets to it, like the structure, the composition, and function of an area. And including evolutionary history allows for prioritization of important areas. And this is where phylogenetic metrics step in. And the most commonly used are phylogenetic diversity and phylogenetic endemism. Phylogenetic diversity represents the minimum length of phylogenetic branches that connect a given set of taxa on a rooted phylogenetic tree, while phylogenetic endemism represents the geographic rarity of that portion of a phylogenetic tree that is found in a given area. The advantages to including phylogenetics in biodiversity assessments, one of them is that they are not limited by geographic boundaries. They include important evolutionary history, like I mentioned, and they're useful for conservation. For example, it has been found that using phylogenetic diversity to select important areas for conservation leads to more protected areas being demarcated. It also allows for differentiation of types of endemism. And these types of endemism are palaeo-endemics as well as the neo-endemics. A palaeo-endemics are taxa persisting in restricted areas that were once widespread. For example, the sequidendron, which was once widespread in the northern hemisphere but is now just restricted to California. Most likely this area supported the sequidendron by having stable environment, thereby forming refugia. Neo-endemics are newly formed taxa that are restricted to specific geographic areas. For example, the Hawaiian silver swords, which came about through adaptive radiation. So Southern Africa is home to about 24,000 vascular plant species, and 60% of these are endemic to the region. There are many protected areas, but these were mostly demarcated using species richness and endemism to establish them. So it is important for us to find out if areas of high species richness correlate with areas of high phylogenetic diversity, so that we can check if the full evolutionary distinctness is being protected in the region. Species richness is usually a good surrogate for phylogenetic diversity, but this is not always the case. There is also lack of information on neo and paleo-endemic hotspots in the region, as well as the phylogenetic metrics are relatively recent to the field and need to be assessed for effectiveness in biodiversity measurements. Therefore, my aim was to assess the role of phylogenetic metrics in identifying hotspots of diversity and endemism for conservation. And to achieve this, my objectives were to calculate measures of diversity, compare effectiveness of phylogenetic metrics to identify areas of neo and paleo-endemism, as well as to assess their representation in protected areas. The study focuses on Southern Africa, which is generally a region incorporating all countries in the southernmost part of Africa. It includes countries south of the Kunene, Zambezi, and Limpopo rivers, and is an area of about 2.5 million square kilometers. It encompasses 3 of Africa's 9 biodiversity hotspots, that's the Cape Floristic region, Succulent Karoo, as well as the Maputoland Ponderland one. So this area forms an ideal region for biodiversity studies. The study taxa chosen for this was the genus Helichrysum, part of the Asteraceae family, commonly known as the everlasting daisy. There are about 600 species worldwide, with 242 in southern Africa. This genus was chosen because they are widespread and many species are highly endemic to the region. They are found in many biomes as the forest, grassland, and fynbos biomes. So to calculate the species matrix, Pretoria Computerized Information System data, which is PRESI data, was obtained from SANBI and the Namibian National Botanical Research Institute. And this data comprises of data from various national herbaria. The data was cleaned before analysis. And to obtain the phylogeny for Helichrysum, sequences were obtained from GenBank as well as Cron and Bag. Phylogeny data was used to root the tree, and there was a 70% genus coverage, meaning that 170 of the 242 species in southern Africa were used in the phylogeny. A Bayesian inference analysis was conducted, and the majority rule consensus tree file was then imported into Mesquite for editing before analysis in biodiverse. 4 diversity indices were calculated, and that's species richness, weighted endemism, phylogenetic diversity, and phylogenetic endemism. And these calculations were conducted in biodiverse. Biodiverse is a software that links visualizations of data distribution in geographic and phylogenetic species and allows randomizations for hypothesis testing. Please note that these calculations were done per quarter degree squared. So to assess the effectiveness of phylogenetic metrics, hotspots were defined as the highest 2.5% values of the grid cells of each category. So this threshold has been used by other authors and in other studies, and it has been shown to be sufficient for delineating hotspots. Overlap was assessed between the hotspots by projecting the output maps in ArcMap and checking for the overlap of grid cells for the species metrics and the phylogenetic metrics. The hotspots were then overlaid on a GIS layer of protected areas from UNEP to check for protection. And then to differentiate between areas of neo and paleo-endemism, a rigorous approach brought forward by Michelle et al. 2014 was used. And this is known as the categorical analysis of neo and paleo-endemism, and in short, CANAPE. This program uses a randomization test with 999 replicates, no replacement, and the diversity values obtained from the randomization test form the null distribution that is then used to compare the distribution of values from the actual diversity indices. And then the cells that do not show significantly high values are excluded. And from the remaining grid cells are classified as hotspots of neo-endemism if they fall into the 2.5% lower tail, hotspots of paleo-endemism if they fall into the 2.5% higher tail, and of mixed endemism if they fall in the middle of the distribution. Mixed endemism means that it is an area where there are both neo and paleo-endemics in one area, while super-endemic hotspots are areas where there are very high levels of neo and paleo-endemics in one area. And for the results, all the data collected comprised of 20,324 records representing 245 species, and Helichrysum occurrence was found to be mainly concentrated in South Africa, with concentration along the eastern Great Escarpment, as well as in Namibia on the west side of Namibia. Species richness and weighted endemism peaks in the mountains and grasslands of Sekhukhneland and the Volkberg in Mpumalanga and Limpopo, as well as in the Drakensberg escarpment in KwaZulu-Natal. Notably, the highest species richness of 110 species was found in central Drakensberg as well as the northern Drakensberg. Phylogenetic diversity almost follows the same pattern in that it peaks in the Drakensberg Alpine Center, the grasslands of Sekhukhune, as well as some areas in Johannesburg and Magaliesburg, shown there in the blue circles. Using the top 2.5% rule, 42 grid cells with the highest values were identified as hotspots for this study. And my maps, I've trimmed my maps to show only the areas of importance. The hotspots identified using species richness and using phylogenetic diversity did overlap in the Drakensberg, Barberton, Volkberg, and Sekhukhune areas, but phylogenetic diversity did reveal additional hotspots in the Tugela, Magaliesburg, and Johannesburg areas. So there was high overlap between the two metrics. Species richness hotspots are well protected in various protected areas, but phylogenetic diversity hotspots were fairly protected, with some areas not falling within, with some hotspots not falling within protected areas, such as in the KwaZulu-Natal Midlands, the southern KwaZulu-Natal, and Swaziland. Hotspots of weighted endemism and phylogenetic endemism overlap in almost the same areas as well. In the Drakensberg, Stanger area, Magaliesburg, Barberton, Volkberg, and Sekhukhune areas. However, phylogenetic endemism metrics also identify additional hotspots in the Johannesburg, Kraddock, and Cederberg areas. Same as before, the weighted endemism hotspots are well protected, but the phylogenetic endemism hotspots, some hotspots do not fall within protected areas, for example, in Swaziland, in southern KwaZulu-Natal, and in the Eastern Cape. For the Canopy analysis, 96 grid cells were found to be significantly high in endemism, and only 4 of those represented neo-endemic hotspots, with 3 of them in South Africa and 1 in the Otjiwarongo district in Namibia. And paleo-endemic hotspots are more widespread in the region, and in terms of protection, neo-endemic hotspots are poorly protected, with only 1 being protected in Namibia and the other 3 not falling within protected areas. And the super-endemic hotspots were moderately protected, with 8 out of the 15 falling within protected areas. So to bring this all together, I found that there was congruence between species richness and phylogenetic diversity. And there have been similar findings. For example, Leite et al. In 2015 found that there was high congruence between species richness and phylogenetic diversity hotspots in a number of Australian taxa. But the opposite is also common. For example, Darrow et al. In 2015 also found did not find any congruence in Southern African trees. And there's a general consensus that congruence is based on the genus, its biogeography, and the history. So the high species richness in the Drakensberg could be attributed to the origin of the genus. It originated in the Cape, then it dispersed to the east and then northwards into tropical Africa. The Drakensberg also offers various ecological niches, just like the Sekhukhune and Volkberg areas, because of the variable topography due to magma upliftment and tectonic forces. There were some insufficient records in some areas, for example, in Botswana. And generally, the isolation caused by the heterogeneity of these environments could have given rise to the high phylogenetic endemism in this region. And the areas with neo-endemics, the areas of high neo-endemic presence were mostly mountainous. So allopatric speciation could be attributed to this high level of neo-endemism. And the super-endemism hotspots were mainly in areas of historical instability. This could have come about, for example, if the instability could have caused patches of vegetation to survive, where the paleo-endemics would then thrive, while the new vegetation and areas would have given rise to the neo-endemics. So in the context of conservation, areas containing neo-endemics are very important because these are areas of speciation, while areas of super-endemism are most essential because they are areas of speciation as well as being refugia for species. There is more conservation needed in many of the areas that I looked at in the region, and phylogenetics facilitate for conservation of the process behind the pattern, as well as offer more information on the biodiversity of the area. And in conclusion, I did find that there was high congruence between the metrics, with phylogenetic metrics revealing additional information about an area, and that including phylogenetics does reveal more information. I also found that CANAPE is a useful tool for differentiating between areas of endemism that are important in the region, and that many hotspots in the region are not protected. Thank you.